Right. Last but not least, Shuo is now going to talk about trustworthy sketch-based telemetry, and he's a second-year PhD student at CMU. So Shuo, the floor is yours.
Thanks for the introduction. Thank you. Hi, everyone. I'm Zhuo. I'm a PhD student from CMU. And today I'm going to talk about the TrustSketch, trustworthy sketch-based telemetry on cloud host. This is a joint work with Maria, Alan, and Vias. So we're considering a cloud setting, like the cloud provider like AWS, GCP, or Azure. They run a lot of servers, and they also manage the network connection between the servers. And periodically, the operator may want to collect network telemetry information from the servers, such as like how much network traffic has been sent between the servers or between different IP address, and so that the operator can use those data for some downstream task, like monitoring if there's a DDoS attack, or for accounting, like charge the user based on the network traffic volume they have sent. And previously, many work has shown that Sketch is a very good tool for the telemetry because it has a low footprint and is efficient and it can provide accurate results. And I will briefly talk about how Sketch works. So considering the operator have such a question that the operator want to know how much data has been sent from each IP address. So this task can be solved by the CountMin Sketch. So there are two stages. The first is the updating stage. So when packets come, we will extract the flow key from the packet, like what is the source IP address. And using the IP address, we would compute several hashes. And the Sketch would also maintain like a counter array. The counter array would record the information about how much data has been sent from each flow. And using those hashes as the index, the Sketch would update several counters, and they would add those counter by one. Means there's one more packets coming in. And the Sketch also maintain like the flow keys, like what are the IP address of the flow key of the flows. So during the query stage, the operator, for example, the operator want to know like how much data has been sent from the IPA. So the operator would follow the same procedure. The operator calculates several hashes using the IP address A, and using those index to query those counters. And here, like they get the number like 15, 7, 12. And for the CountMin Sketch, they would use the minimum number of those three numbers as an estimation of the flow size. So here we just show the CountMin Sketch as an example. There are some other sketches for more complicated tasks. They also using the similar data structure. So many previous work, like from CCOM or NSDI, they propose to run the Sketch on the host. So here is how it works. Like several servers has been connected to a switch. And for each server, there is a hypervisor and several virtual machines. And they propose to run the sketches in the hypervisor as a software. So the benefit of running Sketch on the host rather than like running the Sketch on the hardware switch is that this can provide you like a fine granularity monitoring because you can monitoring the traffic from each virtual machine. And since also because it's software, it's easier to manage and easy to deploy. So in this work, we consider what if the Sketch is compromised? Then we will show like the downstream task will also be compromised. So for example, an attacker used one server to launch DDoS traffic. So the attacker sent lots of traffic into the network. And if the attacker compromised the Sketch, and the Sketch would report that there's no traffic and to the operator. And this is incorrect. And the operator based on this incorrect telemetry result would not be able to detect if there's a DDoS attack or provide like an incorrect accounting result. So normally the Sketch is run in the hypervisor, and the hypervisor is run by the operator. So normally it's okay. But however, like previously, like there's lots of studies show that there are some hypervisor vulnerability in today's data center, such as like VMware, Zing, or SaltStack. And by using those vulnerability, the attacker can compromise the hypervisor, and so they can compromise the Sketch. So our goal is that we want to provide a trustworthy Sketch-based telemetry. So what we want to achieve is that even with the existence of the attacker, we can still like use the Sketch to provide correct telemetry of the in and outgoing network traffic, so that the operator can correctly detect if there's a DDoS attack, and they can also provide correct accounting result. So overall, our contribution is that first, we formulate the requirements for the trustworthy sketch-based telemetry. And we provide a framework called the Trust Sketch, which is based on the Enclave and SmartNIC. And we show the evaluation result that's showing that the Trust Sketch is safe and with low performance overhead. OK, next, first we talk about what are the requirements for trustworthy sketch-based telemetry. So first, we consider how an attacker can compromise a sketch. So suppose the attacker using one machine and from IP address A send to IP victims and lots of DDoS traffic. How can the attacker compromise a sketch to try to hide those traffic? So there are 3 different ways. The first one is that the attacker can compromise the sketch computation. So for example, they can change the code or change the runtime library so that when the sketch updates the counter array, it would not update the counter array correctly for the flow sent by this attacker. And the second, the attacker also can directly modify the memory, like they directly delete the flow key, like IPA, from the flow key stored by the sketch. And the third way is that the attacker can change the input to the sketch. So for example, the attacker changed the flow key from IPA to IPXYZ so that the sketch would think like this flow is sent by someone else. OK, so next we talk about the requirements. So first, for the integrity, we want to make sure the sketch computation is correct. Like this includes the instruction executed by the hashing, the counter array, and the flow keys. And the second, we also want to make sure the memory of the counter array and the flow keys are updated correctly. And finally, we want to make sure the input to the sketch is correct. So specifically, we want to make sure the packet header seen by the sketch is the same as the packet header seen by the NIC. So here we only care about the packet header because telemetry only works on packet header. We do not need to protect the packet payload. And other than those 3 integrity requirements, we also have some other system requirements, like the performance. We want to achieve line rate and with low overhead. And another thing is the operator may have several different telemetry tasks, and they may deploy sketch 1 for flow counting and another sketch for heavy hitter and so on. So we want our framework to be general to support different kinds of sketches. And next, we will show the existing solution cannot meet all the requirements. So here we summarize the 5 requirements we mentioned before and 3 existing solutions. And unfortunately, none of them can meet all the requirements. So for example, the cross-checking is you can mirror the packets from each server to the controller and reconstruct the sketch there and check if the sketch is correct. And however, this would have high performance overhead. And other solutions like code attestation and secure memory, they only provide some static check, and they cannot meet all the requirements. We have more detail about those solutions in our paper. OK, after talk about the requirements, next we talk about our design, like Trust Sketch. At a high level, our framework Trust Sketch built based on 2 roots of trust, Enclave and SmartNIC. So Enclave is a private region of memory allocated by the CPU. And the hardware will guarantee that both the code and the code and data inside of the enclave is protected. So anything outside of the enclave, even the hypervisor or the kernel, they cannot read or write the data or the code inside of the enclave. And the SmartNIC is a piece of a programmable NIC that allows you to run some customized code, like how to process the packet header or so. And the SmartNIC also have the similar hardware protection. And also, SmartNIC is a standalone hardware, standalone from separate from the hypervisor. So even if the attacker compromises the hypervisor, the attacker need to find additional bugs of the NIC to compromise the NIC. So overall, we assume both the SmartNIC and the enclave are protected. So the opportunity here is there is this runtime protection provided by the hardware. And another thing is both of them are already deployed in today's data center. However, there are still some constraints. The first one is today's commodity NIC have limited compute and memory resources. And another thing is the data path between the enclave and the SmartNIC is unsecure. The data path has to go through the unsecure part of the hypervisor. And this is some limitation of today's hardware. Even the latest generation hardware have this problem. OK, so given those opportunity and the limit and the constraint, we consider how can we design our system. So the question is, the first question is where to run the telemetry system. So overall, the telemetry system have like 3 components. The first one is a sketch. The sketch would maintain the telemetry data. And the second component is the virtual switch, which take care of like updating and forwarding the packets. And the last one is the I/O interface, which is like a glue bridge between the software network application and the hardware NIC. So we can run those components in those 3 different places, like enclave, host, and smart NIC. So where do we run the telemetry system? So before we present our approach, we first show 2 strawman solutions and explain why the simple solution do not work. So here are the 5 requirements we mentioned before. The first strawman solution is that since the NIC is protected, we can just directly run the sketch in the NIC and leave the other 2 components in the host. And this would provide all the integrity requirements. But we mentioned before, like the NIC has like a limited compute and memory resources. So it may not support some sketch if the sketch like need to update multiple counter arrays or so. So this fails the generality requirements. The second strawman solution is that since enclave is protected, we can just run everything in the enclave. This would also like provide all the integrity requirements. However, like both the virtual switch and the I/O interface, they have lots of system calls, which has to be executed in the host. So there will be lots of transition between the enclave and host. So this would have high performance overhead. So finally, is our solution. We only put the sketch in the enclave and leave the other 2 components in the host. We identify like the sketch is the critical component to provide the correct telemetry result. However, like as we mentioned before, like the data path between the enclave and the smart NIC is unsecure. So this does not provide input integrity. So next, we talk about how we leverage smart NIC to ensure the input integrity. So we assume like there is a shared secret key between the NIC and the enclave. So when packets come in from the outside into NIC, the NIC would use the key to calculate a MAC based on the packet header. And then the NIC forward both the packet and the MAC to the enclave. And then the enclave can use the secret key to recompute this MAC and to check if those 2 MAC are same. And if the enclave find like there's an inconsistent MAC, the enclave will know like there's an attacker, and the attacker changed the packet input. And similarly for the outgoing direction. So here we assume like there is no packet loss or reorder without an attack between the enclave and smart NIC. This is because all the packets between the NIC and the enclave are stored in the software buffer. So we can just allocate a very large buffer to ensure like there is no packet loss or reorder. And another thing is like we need to compute like separate MAC for both for incoming and outgoing traffic because the traffic rate could be different. So however, there are still some challenges need to be solved. Like how do we handling this multi-thread NICs? So today's modern NIC, like they use multiple threads to process packet to improve the throughput. So for example, when the packet stream comes, like P1, P2, P3, the NIC would divide those packets among different threads. So here we show that thread one would process P1 and P3. Thread 2 would process packet 2. So each thread would compute the MAC based on the packet substream that thread seen. And later the NIC has a reorder buffer. It would reorder the packet to ensure like the packet order is correct, like P1, P2, P3, and the MAC in the between. However, when this packet stream arrived the enclave calculated another MAC. When enclave calculate the MAC, like the first MAC is, the enclave would think like the MAC is based on P1, P2. But actually that MAC is, when NIC calculate the MAC, that MAC is based on the packet 2. So there would be like a mismatch between enclave and the NIC. So our solution is that we tag each packet so that we can reconstruct the substreams. So when NIC sends out those packets, they add a small tag to each packet. And that tag contains the thread information, like which NIC thread has processed this packet. So when the packet stream reaches the enclave can reconstruct this packet substream based on the tag. And this would ensure like the consistency between the enclave MAC and the NIC MAC. Okay, next we show some evaluation results. So first is the security. Like we model 6 different kind of attacks, like the attacks cover both the compute and memory and the input attacks. And we compare our framework trust sketch with 2 baselines. The first is the baseline, like how the sketch is deployed today, which is unsafe. And another baseline is like a safe break, this is a previous work, and they only use the enclave and does not provide the input integrity. So the result shows that both the baseline and the safe break, like they can be compromised by some attack, and our solution, like TrustSketch, can protect against all kind of those attacks. And next, we show the performance result. This shows the throughput running over like 4 different kind of traces. And we show that compared to baseline, like TrustSketch has an overhead about 7%. And if you look into detail, we find out like most of this overhead comes from the input. When we provide that input integrity, we compute MAC. Most of the overhead comes from computing MAC. And we consider that if the next generation enclave or NIC, they support a special instruction for computing MAC, we can further reduce this overhead. And finally, we show the accuracy result. We run the sketch for 4 different telemetry tasks, and we show what is the accuracy can be achieved by both by the baseline system and the TrustSketch. And we find out like TrustSketch has the same accuracy as the baseline. This is because we do not need to modify any code of the sketch. So overall, my talk shows that the sketch are attractive for resource-efficient telemetry in the cloud. However, like if you deploy them naively, like the sketch can be compromised by the attacker. And our work, we formulate the trustworthy sketch-based telemetry problem, and we provide a framework called TrustSketch, which is based on the enclave and SmartNIC. And we provide evaluation results shows that TrustSketch is safe and has low performance overhead. That's the end of my talk. I'm happy to take questions. Thanks.
Thank you very much, you. Very nice talk. So we have time for some questions. Yes, please state your name and affiliation.
Hey, Manuel Egele, Boston University. Very nice talk. So I have a question with respect to your threat model. You have to do a little bit more convincing, for me at least. You assume that the adversary can break out of a virtual machine and compromise the hypervisor, but the adversary cannot compromise whatever you're running on your SmartNIC. Now, my understanding, looking at whatever Bluefield SmartNICs, they just run an off-the-shelf Ubuntu installation anyways. So why do I assume that you can compromise the hypervisor but not the SmartNIC?
Oh, okay. There are like 2 reasons. One thing is like many of those NIC, they have the hardware guaranteeing that the code and the data are protected. And another thing is like we assume because the NIC is like a standalone hardware. So even if the attacker compromises the hypervisor, since the NIC is a separate thing, the attacker need to find additional bugs of the NIC so that they can compromise the NIC. Yeah.
Eddie Treu from KU Leuven. About the keys for improving the path between the enclave and the SmartNIC. Is there also encryption going on? And if so, at which protocol level?
Sorry, say that again. What's the last sentence?
Is there encryption going on? Is there encryption implemented using the key that is shared between the enclave and the SmartNIC?
No, we only use that key to compute the MAC. And the key can be negotiated during the bootstrap stage and also update periodically later for better security. Yeah.
I thought there was a confidentiality requirement, or did I miss that?
Sorry?
I thought that in your requirements there was a confidentiality requirement.
No, I think mostly we want to provide the integrity rather than confidential.
Okay,
yeah.
Sorry.
Yeah, thanks.
So we're running a bit out of time, so let's thank you again.